Okay, then let's welcome another Professor Wang, Chien Wang, who will give a talk on anthropogenic aerosol effects on cloud and precipitation. You can take as much time as you want. You can take my time.
I won't. Yeah. I guess first foremost, I want to thank JP. Our friendship go back to a very long time ago. We had a gun of 4 at a C4. So, and also other organizers for having me here. Apologize, the format is the Mac produced. Anyhow, I'm just here as a reporter. The work's done by my generation postdoc and contributed by many colleagues in here. I'm going to go through a rather odd aspect of looking into the aerosol climate impact. It's mainly focused on the cloud and the precipitation in a global scale, the climate scale, or what do we see? Okay, so this will be okay. So you've probably been already exposed to all these kind of charts before. What the aerosol can do, what aerosol means to climate forcing. So basically, people at the past believed one is the direct forcing, which is the aerosol itself can, scattering solar radiation, and there's some long wave, but I'm going to focus on the short wave again. So, and a certain part of aerosol species can also absorbing this short wave radiation. So overall, both effects will reduce the surface, incoming solar radiation, and leave a persistent forcing to the system. So why we call it forcing is because these are anthropogenic aerosol, which doesn't belong to the natural system before. Anyway, so aerosol is a fundamental reason, or some people argue it's one fundamental reason. I think that's a fundamental reason for the cloud to form under current climate, because that's provide an existing surface. So naturally, our view goes to what this this effect will do to the cloud, because all the cloud droplets basically activate on the surface of aerosol. So these are called indirect forcing. Actually, should be direct effect. But anyhow, that's just a term. And there's also other things. In recent years, some people call it semi-direct, because aerosol perturbate the thermal profile in the local, and that might affect also cloud. Why cloud being a central issue? Because the cloud radiative effect is still very, very large compared to aerosol. So, well, I want to, I find myself rather radical in this field. So my view is general to the cloud and precipitation itself, rather than just thinking as an odd term, as a forcing. So I see this, generally it's regarding the cloud and the precipitation, the aerosol really just, you can call it the microphysical passes through all these activation things and form microphysical properties of features of a cloud and also precipitation. Another is, if you have a direct effect, you're staying in the atmosphere. A recent study already proved. So this effect can coupled with the dynamical process and also effect of cloud and precipitation. I'm going to generally go over this direction in my talk. So that's the most dynamical field in my point of view. And there's create a lot of work recently. Notably, if you change the cloud itself, then that through the microphysical path, that can also couple with dynamical process and form so-called fit into dynamical paths. So this is a concept that is really not self-consistent, rather than very wide meaning here. So it's really interesting, actually. So, okay, here's another Mac and a PC thing. Why does it become a 10 number? Anyway, so generally, what I'm trying to say here is that, if you consider climate response and the feedback to the aerosol, you have to have a global model. So the regional model does not solve that in the end of the day. So here's the current option. What do we do in the global model? So first consideration is the atmosphere transport model. This is actually a model driven by known meteorology. So this generally describe aerosol distribution rather than response. So this actually millions of dollars and decades effort actually contribute to this, but this turned out to be not really useful to for our purpose. So basically, you can see two type of things modeling being used in the climate study. So one thing you can prescribe the aerosol forcing in a climate model. Recall majority of IPCC modeling the AR4 and the large fraction of AR5 models still use this. So you basically prescribe the climate response to aerosol without consider feedback. So I'm going to concentrate on third. That's my group's work in the past decade. So we consider interactive. Really, you put a response and with feedback together. Well, there's a few considerations because you're doing the climate modeling. You really have to consider computation issues. It's a long integration because there's a requirement for the ocean component to settle. And why, in the same time, you have to consider aerosol representation. What's among these basic elements you can describe the aerosol? The first come to the mind would be size distribution. So here's a measured, roadside aerosol distribution. You can see here is the generally 3 mode. It's not always, right? So, but you can see it's rather sophisticated, actually, 3 general mode. That's a number mode. So people invent various methods to describe this in a model. Certainly, I put it here beam model. Actually, it's a beam model for aerosol does not exist because it's too computationally intensive. You can consider the aerosol can cross 3 order of magnitude in terms of size. So beam is a totally wasted resource, and statistically it's against the measurement. That's a long story. I can give another talk. So it's a slightly more advanced, or not so in theory, is a so-called section model. People usually build a 10 or a few more sectional. So they sometimes let them to move along the major size center. More, makes sense in computational and representation-wise. The balance is a so-called modal or moment. So here you prescribe the field distribution, use mathematical function, or you use the integral to close. So that's called a moment or a modal. So this aerosol distribution, access distribution, actually is a stochastic concept. I don't know how much people are interested on that. So we know this skill for a long time. We know how to predict a moment without touching the real stochastic nature of that. Well, certainly in the end, and people in the majority of our aerosol model actually is a moment dispersed, or so-called a single moment model is only consider mass. So actually they had a few mode and consider these aerosol inside these mode would be having same size distribution. So this is a kind of a yesterday already. Now the more things to bring up on the table. So here's a more chemistry or physics. It's called a mixing state. This is just our I just use our model as a example here. So when you have a black carbon, and this is generally installable things. So once you have inorganic acid or other matter, they will form a shell. So they'll create a very strange, very interesting subject in terms of optics. So you can see this. In the top, you can describe the aerosol extinction. It's a mass extinction capacity, and here is just a different curve, just showing the core and the shell ratio. So going from high to low. So very similar, and you can see this being enhanced a little bit. But most interesting is the so-called single scattering albedo, which is a fraction of scattering portion to the total extinction, or 1 mass this would be absorbing. So when you have an absorbing core, so you can see you only need a tiny little, maybe 30% of cost in a mass, then you immediately form a very nonlinear. So you make a huge monster, and so very strong in the scattering and also absorbing. So there's other consideration, including my microphysics part. So in the past, or here just an example, you can describe the size distribution, and without chemical and microphysical reason, these different colors just used as showing different type of aerosol species or aerosol combination. So this is a size resolving only method. You pile them together into a size distribution without knowing certain chemistry and microphysics behind. So this is a new thing. So actually they should grown by themselves, and they can transfer only when chemical process or physical process exist. So this is the new way to describe the two-dimensional way to think about this size and mixing. And here is another minor example. This is my group's work, one example of these. So we have six mode or 6 different aerosol here supported by sulfur gas and aqueous phase reaction. So you have a 3 external mixture of the sulfate separate from nucleation mode is a few nanometer. Then to argon, so our argon is rather 10 nanometers, so all the way to the accumulation. And you also have external BC and OC, so you can define this. There is still argument on that, but basically they are there, and they can also grow into the mixture. So here's BC and a sulfate. This is a core shell. And here OC and a sulfate will let them mixed rather well mixed. So there's a lot of things you can see there. You can read our papers. They're really long paper. Well, certainly the first thing is how why you spend that much time to do that. You have to evaluate your model. These are just this is our modeler's chart to compare against the observation. So here is just two. This is an annual base. This is a monthly base. So we compare to the modes and also 74 aeronaut station over the globe. This is a log. So part above this is aerosol optical depth is a total extinction. Here's the absorption part, and it's an annual. So you can see our model are at least not necessarily worse than anyone. So if not much better. And our model also describes the size distribution because we do a 2-moment scheme. So this is a much more challenge. You can compare. You can see the comparison against neural networks and number concentration. Sometimes good, sometimes it's just not too good. So this is a recent work we just published last year. I think we compared to the commercial aircraft mounted transatlantic measurement on the aerosol. Well, this is a measurement. This is an aerosol. Obviously, I made the color, favor to the model comparison. Okay, so I want to switch to one really interesting topic. So my group has spent a lot of time, and I also myself was really interested on this. It's absorbing aerosol, anthropogenic absorbing aerosol. This is a really, really, really interesting project. So this things actually create a very interesting distribution of the forcing. So in the atmosphere, because there's heating, so this is a global mean and an annual mean. So this 1.5 rough watts per square meter heating to the atmosphere is persistent, global mean, okay? The local is much, much larger. So at the surface, it also causes cooling because the warming is a little bit larger than this because the model is scattering of the low cloud. And in all, there's a residual about 0.5 watts per square meter warming in the top. So a lot of people think in the sun in the past saying that global warming, and now it's pretty much quiet down. But however, this is really funny distribution is really we're seeing across all these climate forces. So that's why we spend a lot of time on that. Oh, I just mentioned, I forgot to mention the climate sensitivity to this aerosol is really different than the CO2. It's much lower, but it doesn't mean you will see it now. It doesn't create other effect. So here's a really bizarre chart. Actually, this came from many century-long integration. Each of the integration only include emission from one continent, like East Asia, Europe, North America, South America, and the rest of the world. And the TE is a all emission run, which include all these emissions in the one run. So you can also do a summation of summation of all these runs result, and this does not exist, that run, right? So this is a huge increase. What you see here is a precipitation anomaly as a zonal mean case compared to without aerosol. So you can see in the simulation include all these emissions. Actually, it's a thin black line here. Compared to you arithmetically add all these individual runs that only contain one continental emission, you can see this difference. This is showing nonlinearity in the climate response. This is a very long story, so I have a paper there, and I on purpose published, hold the paper for quite a few years. It's a little bit sensitive. Another topic that I just want to use as example is a recent work. Many group, including mine, did this. It's to the Asian monsoon. Actually, mostly Indian monsoon at this moment. So I contribute to that bizarre piece a little bit. So a lot of argument and there's certainly a large general public interest on this. I do see the Taiwan's interest as well, but East Asia monsoon is much more complicated. So it's a really big deal. People argue there. So here you can see the model result of all these absorbing aerosol optical depths. It just take as a measure of absorbing strength over India. So this is a longitude and latitude shot. You can see during the pre-monsoon season, there's a huge, because it's dry season, so huge loading there. And during monsoon season, it's somewhat diversified because of the rainfall. So if you see this in the zonal mean over region, you can see this loading it's just basically over Indian subcontinent and along the slope of plateau. And here, so this is a misreading. If you do the zonal mean, you think there's loading above the plateau. Actually, it's here and here. And you can see this actually from the CCliCS. It's really by luck, actually. CCliCS doing the, this is from south to north. Actually, CCliCS is here, is north. So this is a plateau. So this is the aerosol layer. So the general interesting is what this do to the monsoon. There's many other groups of work and different hypotheses. Here, since I'm giving talks, so I just only show ours. So what you see here is also a precipitation anomaly. We run quite a few cases. The first is only include both scattering and absorbing aerosol. And secondly, it's only include absorbing aerosol. Here's only scattering aerosol. Here's a long-term land-based CRU measurement. This top panel is pre-monsoon. Here's the monsoon season. So you can see there's a shocking similarity between these two runs, include absorbing aerosol. So basically, you have a rainfall pattern shift toward north and the northwest. Actually, cross into the Pakistan areas also. And also in the land area, consistent with the observation, you can see this reduction there. So and as a contrast to this, the scattering aerosol case gave a very different feature. Certainly the monsoon season is a little bit more complicated. I don't think aerosol is the only reason here. Obviously, other people had a different hypothesis. My hypothesis is based on a moisture static energy. So this is a general structure of a so-called this lower below cloud layer, moisture static energy. The dynamical series actually radiative equilibrium theory, convective equilibrium theory will tell you also most vulnerable, most sensible places across this, zonal. The latitude gradient is a 0 place, so that's a very sensitive place. And aerosol forcing happen here. So this is a long story. Can read the paper. So that's why it caused this north shift. So there's a right time and a right place. And recently we also did some other analysis we just published on the journal Climate. I think it's still online. So here, this is a little bit busy chart. So these are, okay. So I think this is a on-site time pentet is every 5 days. So actually on-site. So you can see from on-site from here to here. And here is a different loading of we consider both warming and this is only warming. Here is only surface cooling, and this is both. So you can compare the on-site time. Actually, this is a difference. So blue color means advanced, so it's a minus. These with a cross shown the statistical significant area. So here is a much more easy chart to read. It's this start from pentest 32. So we define one odd quantity called on-site central, which is a line. It's a center point of a line across the Indian subcontinent. So you can see, this compared to this reference run here is all these three runs with aerosol forcing will move much faster, which means it's not on-site being advanced, and also the moving is much faster. The last story I want to tell is very important, the nonlinearity. So when your aerosol have two opposite forcing here, so you naturally your interest is going to whether combined effect will be very different than you linear overlapping the warming and cooling effect. So this is just a case that showing here is a large nonlinearity. It's due to the fact that they coexist together. So we are still working on that. Let me just wrap up very quickly here. A few points is anthropogenic aerosol affect the clouds can through both dynamic and macrophysical paths. And current knowledge are very new, still new. So we believe dynamic paths can create a much larger effect than macrophysical effect on precipitation. Okay, so both direct and indirect can contribute to the dynamic path. We have to concentrate on, focus on some nonlinearity issue. I believe this is not just aerosol itself, also aerosol and greenhouse gas forcing combined effect. And you already see this. So we see persistent forcing. In particular, absorbing aerosol can cause a change to some critical tropical system like ITCZ and monsoon. So thank you.
Okay, thank you. So we should really thank Joyce for not coming. Otherwise, we don't have enough time.
I might change a little bit of my topics if it's here.
Okay, questions?
Yeah.
Xiao first, then.
Yeah. Very, very interesting talk.
Okay.
And we compared the data both in Taiwan and over mainland China. Compared, say, to Taiwan industrial development, pretty much in the 70s. And in mainland China, it's about 10 years later in the 80s. And we compare pre-development and after development, and hopefully to see the aerosol effect. We saw zero effect. Okay?
What do you mean zero? It's the mean
Just we don't see anything in terms of precipitation. Sorry, I was commenting about your impact on the Indian monsoon. Okay?
Yeah.
And not only that, but we compare eastern Taiwan to western Taiwan and compare the summertime precipitation. Again, there's a zero effect. Identical. The two sides are identical. And we know the east side is very, very clean, especially in the summer. And the summer and the western side of Taiwan is polluted.
Okay. Yeah. Oh, yeah. I guess probably this is not really surprising actually for the regional. So I didn't really really take much time on explain the feedback issue. That's why if you think about a microphysical effect, we naively at first, I did a lot of cloud resolving model actually, and many other colleagues. So eventually we found that if you integrate a system along, you might not see any effect in the precipitation. The reason has been very, very simple. Precipitation is sitting in the bottom of food chain of all these water cycle thing. So there's a lot of dynamical feedback can compensate initial microphysical effect to create a difference. But whether there's a climate effect, that's very different, because quite often the dynamical path why it amazes us is because that can occur at long distance from aerosol laden region. So there's a very, very large scale effect there. And I can point to many other evidence. We do see these evidence, and also model indicate. For East Asian monsoon, also specifically for East Asian monsoon, the result is much contradictory to each other than the Indian monsoon. Indian monsoon, all the groups, at least 10 of them, and also the local analysis, many rainfall analysis, all indicate there's evidence on that. Because I'm part of this assessment report team. So that Indian monsoon story is pretty easy. The East Asian monsoon is very, very different. There's only a few groups had working on that, and they all contradict to each other. The on-site and there's 4 on-site stages. Dynamics involved it's much more complicated than the classic Indian monsoon.
Okay.
So it's
Okay, Hong Xiong first, then Paul.
Yeah, can you say a little bit more about why the aerosol make the onset earlier?
Oh yeah, there's a basically a dynamical perturbation there. It just change a little bit of the circulation. There's a paper on that. So there's a jet being caused and it tweets toward a different direction, and the water supply and being affected. And another basically issue is moisture staggering energy things. The large scale stability being changed. So because of the forcing, in the dry season,
Paul?
Okay, I have a question about the parameterization.
What? I'm sorry.
Parameterization.
Okay.
A lot of people take these observations and form a combination out of it. Now the problem is in observations they often take the size as the aerodynamic size, so it's just equivalent spherical size. Now when you talk about the radiative properties, the shape could be very important.
Yeah.
So you have the same size distribution could have very, very different radiative impact.
Excellent point. I usually make a claim before I say is we totally ignore the size when the aerosol. So that's I totally agree
mean
with
the
you.
shape?
But that's really you introduce another very complicated dimension. But we say that with a certain confidence. Actually, there's a optical measurement showing that's still a fraction effect compared to other two. Size is very, very dominant and a mixing state.
Okay, thank you.
Sure.
Thank you.